Mold tool and die design is a very complex and specialist subject, traditionally requiring complex and specialist tools that are strong in these areas and not in others. SolidWorks addresses all these shortcomings by combining the power of a robust, fully featured 3D CAD solution with all the tools needed to take native or imported parts direct from the customer and produce fully detailed 3D inserts and mold components ready for CNC machining and with complete 2D documentation. Working with different customers requires flexibility when it comes to accepting different file formats. SolidWorks imports a variety of different 3D CAD formats, some of which are neutral formats such as Ejection or STEP, and some are native CAD system formats such as ProEngineer or Unigraphics. The file format that toolmakers have been forced to work with over the years is Ejection, and geometry errors are commonplace. SolidWorks automated repair tools will detect and fix most of these errors before you even see them. If we switch this off, we'll see the sorts of things that can cause problems further down the line. What we're looking for is an enclosed solid body, but here we see a surface has been created, indicating that there is a problem. So we'll just run some diagnostic tools to discover what those problems are. If we zoom into these areas, we can see some gaps which have been caused by inaccurate surface trim boundaries or surfaces missing completely. We can fix these up manually, but instead we'll just let the SolidWorks automated repair tools do the job for us. Within a few moments we get the green light and we can proceed with the design. Now the first thing we'll want to do is interrogate this design to work out how we're going to make it. SolidWorks comes with many useful tools such as a parting line check and an undercut check, certainly useful when determining if the part can be made and if we need to quote more time and cost for the job. This design has 3 undercuts, so already the price has gone up. The draft analysis will tell us if the geometry is suitable for moulding, if the pull direction is correct, and if there is enough of an angle on the walls to eject it out of the mould easily. Yellow is not a good sign. This tool is so interactive though, simply changing the draft angle or the pull direction immediately updates the graphics. We can also continue working with this graphics display on until we're satisfied that we've resolved the problems. Rather than ask the customer to make the change and wait for the new file to be resent, we can let SolidWorks make the changes for us. To add draft to the faces of imported geometry would normally be very difficult because of the fillets all around them. SolidWorks can take these fillets and remove them, automatically trimming up the surrounding geometry. Now we can treat it just as if it were native SolidWorks model and add draft and fillets as we please. As soon as the draft is applied, the yellow faces disappear, indicating that we have satisfied our design criteria. Re-adding the fillets completes the task. Finally, based on the customer's specified material, we can add a scale factor to account for the shrinkage of the material after cooling. The parting line feature will determine which faces of the model belong to the cavity and which belong to the core. By default it will take the outermost boundary, but we also need to close up any holes. The automated shutoff surface will find these holes and apply boundary conditions at the edges. If a complex shutoff face is needed, these can be made manually and used as required. The same applies to the parting surface, which will be used to separate the two halves of the mould. If the automated tools don't make the shapes you want, you can make them manually and just add them to the folders to designate what types of surfaces you have created. For example, if we take a look at the surfaces in the core side of the mould, There is a surface there that could be extended and used as a parting surface. So we'll just switch over to the surfacing tools and get to work. We can easily remove the trim boundary of the original surface and then trim it back to match the existing geometry. To save a little time, I've already created a number of sketch profiles that we'll use to complete this design. The first sketch will trim back the parting surface closer to the edges of the part, and the second will be used to define the size of the tool insert. But first we just need to drag the newly created surface into the parting surfaces folder so that when we ask SolidWorks to split the mold, it already knows what's what. Since the parting surface is smaller than the insert, we'll make an interlock surface automatically. And there we have the core and cavity of the mold. These can now be used directly for CNC machining. SolidWorks partners with best-in-class solution providers in many different disciplines, such as computer-aided manufacturing to provide the toolpaths to drive your CNC machines, plastics flow and cooling simulation to validate the mold design before it's made, or automated mold-based creation wizards to speed the design process. Whatever your requirements, there is a host of completely integrated and seamless solutions available. Since the external faces and edges of this part must not be marked, we cannot use a hot runner system to directly inject the plastic onto the top surface, nor can we feed on the outer edge, so we must feed from underneath with a subgate. Commonly used features and components can be stored in a library and reused over and over again. For this design, we'll add the sprue, runners and subgate all in one go. Just a couple of references are required to place the geometry, and now we have reused some standard mold features which we can easily modify to suit the current job if required. The undercuts on the snap fit features will need to be removed with a side core. Again, we have a sketch provided, which we just need to edit to attach it to the geometry. Turning off the shading is a quick way to see all the hidden detail. Once done, the core feature creates the side cores and the corresponding cutout in the mold core at the same time. To visualize this easier, let's just move the mold core up out of the way. Since these will be sliding in and out, we must ensure there is sufficient draft on the sides of all the sliding faces. Using regular SolidWorks features, the fine detail, which is prevalent throughout mold and die design, can be easily achieved, and since we're working entirely in 3D, we can be sure our design is accurate and works exactly as required. The other undercut feature must be made with a lifter, which we'll create from scratch. Turning off the shading again, we can see the finer detail of the hook, which we can reuse by copying the edges that we need. This will ensure that the geometry is accurate and will update automatically if a change is made to the design part. Sketch in the rest of the geometry and add some sizes. Then create the lifter using the core feature. At this time, we may also want to consider the best way to eject this part and the best locations for our ejector pins. A simple hole can be created in the core side of the mould to locate the first ejector pin. Using a sketch with points to represent the centres of all the other pins is a quick and easy way to add these features. We'll create the pins in the mould base assembly later. Finally, we may want to add some core pins for difficult to machine areas or for where extra strength is required. This is done in exactly the same way by creating the main shaft and the heel of the core pin using a sketch and the core feature. These then just need to be joined together to make the finished core pin shapes. It's that simple. Up until now, we've been working solely on splitting the surfaces of the mould up into its constituent parts. To place it into a mould base, we can save the parts we need into a separate assembly. This is just a convenient way of ensuring that all the parts are assembled together in their correct relative locations, but then can also be separated into the correct halves of the mould base assembly as required. Before we do that, let's take a quick look at how we can make electrodes for electrical discharge machining. Small features which are difficult to machine, features which need sharp corners, or features which need a cosmetic finish are manufactured using spark erosion techniques. To create an electrode, all we need to do is sketch out the required shape and then let SolidWorks match the profile of the cavity. Once this is done, we can easily add a spark gap and a further offset to allow for any XY orbital motion that may be available on the EDM machine. The electrode will then be set down in Z by this additional amount. And of course, the electrode remains associative to any changes in the geometry. This mold